In this video, in section 13.4, we're going to talk about second order partial derivatives. Okay, so just to illustrate the idea, let's look at the following example. So we have the function f of xy is 2x squared minus 3xy plus 5y cubed. Okay, this is the same function from problem number 1 there on the worksheet. And so we'll start by just computing the first order partial derivatives. And just like we did in 1 part A, right, the x derivative here would be 4x and then minus 3y. And then I'm going to go ahead and take the y derivative of f. And for that, we're going to get a 0 from the 2x squared. Then we're going to get a minus 3x. And then a 15y squared. Okay, so these two derivatives, these are what we call the first order derivatives. Okay, but as you recall from Calc 1, right, if you take, say, a first derivative, then you can differentiate that function. And that's going to give you what we call the second derivative. Well, we're going to do that same thing now, except since there's an x and a y derivative, there's a little more variety in terms of what types of derivatives we can take. Okay, so for example, I could take the x derivative of the x derivative of f. Okay. So what is this going to give us? So here again, I have my x derivative of f is 4x minus 3y. If I differentiate that function with respect to x, I'm just going to get 4. Okay. And now one comment here about notation. So typically with second order derivatives, we abbreviate this left-hand side as the following. So we have a del of del f. So people write del squared of f. And then on the bottom we have a del x. So that's like parentheses del x squared, but people typically don't write the parentheses. We would just write this as del x squared, and this is equal to 4. Okay, so that would be what we'll call the xx derivative. What else could we do? Well, we could take, say, the y derivative of the y derivative of f. So if I differentiate this function up here in blue, the y derivative with respect to y, that's just going to give me a 30y. And again, notationally, okay, the left side will be written as del squared f del y squared. And that's equal to 30y. Okay, but that's not it, right? For example, I could take the x derivative of the y derivative of f. Right? This is another possible second order derivative. And what's that going to give us? Well, if I take the x derivative of this function in blue, that's going to just give me a negative 3. And again, notationally, we can write this as del squared f over, and then on the bottom, we're just going to write del x del y. Okay, and we got negative 3 here. Okay, and then just as well, we can go ahead and take the y derivative of the x derivative of f. And so what's this going to give us? Well, if I take the y derivative of this function up here in green, I get, well, negative 3. And notationally, this would be written as del squared f over del y del x. and this is -3. Okay, now these all together are what we call, so all four of these derivatives are the second order derivatives. And of course, you probably will observe that these last two, okay, where we have del x del y in the denominator and then del y del x, these are what we call the mixed partial derivatives. So the mixed partials. And yeah, notice these are the same thing. So inquiring minds want to know, is this always going to be the case, or is this just some fluke, right? Did I just cook up this example so these two mixed partials are always the same? So here they are equal, at least for this function. Okay, so yeah, is this always going to be the case? And it turns out that the answer is yes, at least for sufficiently nice functions. Okay, so there are some technical conditions here on the function f that need to be satisfied. Now for us, when I just say something like a function is sufficiently nice, you can just assume, right, this will always be satisfied for us. Okay, you have to work fairly hard to cook up an example where the mixed partials are not equal. It certainly can happen. Okay, so always be satisfied for us. But yeah, as long as your function's sufficiently nice on an open set D, so some domain, then yes, your mixed partials are going to be the same, okay? So this is nice for a number of reasons, as we'll see coming up. In particular, you know, if you're asked to compute all the second order partials, it just, you know, as long as your function's really nice, which again will always be the case for us, then it just cuts down on one of the mixed partials you have to compute. Once you know one, then the other one's kind of a freebie, right? All right, so the last thing then I want to say is just some notation here when it comes to subscript notation for the second order partials, okay? So one way I could write, say, del squared f del x squared, the xx derivative. Okay, this is saying the same thing again as this is the x derivative of the x derivative of f. And on the right hand side, okay, we would first take the x derivative of f and then differentiate that again with respect to x. Okay, and then of course basically the same story for the y derivative. Okay, now this gets a little more interesting when you have the mixed partials. So like for these last two here, okay, on the left hand side, as we said before, you just read this notation from left to right. That's the x derivative of the y derivative of the function f. What's a little bit annoying here, honestly, is that when you use subscripts, notice this order is reversed. Okay, and so the reason why is because when you use subscript notation, okay, the way this is read is that, okay, you do here left to right the y derivative of f, and then we're applying the x derivative second. Okay, so I just want to make sure to highlight this because it can get confusing. Now, of course, because the functions we're going to be working with are essentially always going to be nice, Clairaut's theorem will kick in. Even if you were to confuse these two, fyx and fxy, they're going to come out to the same values, so we're probably going to be all right anyways, at least numerically, okay? But all right, that's a good place to stop, and we'll look at some more examples in the next video.